This is Abraham, and Abraham is a man of honor. When Abraham walks into a restroom with 7 urinals in a row, he will pick the urinals very carefully because he knows there will be consequences. Let's say Abraham picks the middle one, the 4th urinal. This is what will happen. The second dude, or the second peer, will pick one, well, definitely not next to him. It's a crime. Nobody likes to pee next to each other. So he will try to maximize the distance. He will go to the first one. And the third peer will do the same and picks the last one. Now, the urinals are basically saturated. The 4th dude, the 4th peer, will definitely violate someone's privacy. So, not a good idea to pick the middle one. So our man of honor Abraham carefully picks the 3rd one. What will happen? The second peer will pick the rightmost one because it maximizes the distance. How about the 3rd peer? The 3rd peer will either pick the 1st one or the 5th one. I prefer the one close to the wall, so I will pick the 1st one. Then our 4th dude can pick the 5th one. By simply changing from the 4th urinal to the 3rd urinal, our man of honor allows one more peer to pee with some privacy. How does this work? Is there an optimal strategy for our man of honor to help more peers to pee with privacy? What if Abraham still wants to obtain the longest privacy possible for himself? Or it's actually possible to help more peers to pee with privacy while keeping the longest privacy for himself. What you just saw is a variation of the urinal problem. In a paper published in 2010, 2 professors studied this problem thoroughly. But different from Abraham, the man of honor, most of us would prefer to minimize the chance that someone will occupy a urinal beside us. From both academic research and our daily experience, we know that personal space is very important when you pee. In this paper published in 1976, 3 psychologists studied this phenomena with a field experiment. This is how they did it. In a field experiment conducted in a men's lavatory at a Middle Western US university, subjects were randomly assigned to one of 3 levels of interpersonal distance. Men who entered the 3 urinal lavatory to urinate were forced to use the leftmost urinal. A confederate was placed immediately adjacent to the subject, 1 urinal removed or was absent from the lavatory. An observer stationed in a toilet stall timed the delay and persistence of micturition. This is a mixture of brilliance and brutality. The psychologists found out that, on average, if you are next to each other, it took you 10 seconds to start peeing. If you have some private space, 7 seconds. If you are the only one in the restroom, 5 seconds. The clear downward trend line indicates that privacy has a profound impact over peeing experience. We can now define the urinal problem formally. There are n unoccupied urinals in a row. You are the first one entering the restroom to choose. Your goal, not Abraham's, is to minimize your chance to have a neighbor. Abraham is a man of honor. His primary goal is to help as many peers to pee with privacy as possible. To simplify or idealize the problem, we need a few assumptions. The first assumption is that the fellow peers will come at a fast, constant occupying rate. The second assumption is the maximizing distance behavior that you already saw. So let me explain these 2 assumptions briefly. How fast is fast? peers come in so fast that you won't be able to finish peeing before all the urinals are fully occupied. Otherwise, if you leave halfway, the problem is no longer well defined. The occupying rate is also a constant. Why? Because the question asks for the chance, but chance is ambiguous. So by introducing a constant occupying rate, we can measure the time or the number of peers when your privacy is violated. The maximizing distance behavior assumption is also crucial. It basically ignores distance factors like the distance to the door. There is an edge case though. If there are multiple equally good urinals, the next peer will pick a random one of them. In a moment, we will prove that this random choice doesn't affect the total number of happy peers with privacy. We are ready to start our analysis, but one last thing before we start. Let me introduce Dave. Dave is not like Abraham. He is very shy. He always chooses to pee at the end. To quickly summarize, Abraham's goal is to help more people or more peers to pee with some privacy. He also hopes that by doing so, he himself will get more private time. While Dave, on the other hand, is very simple. Dave just goes to the end and hopes that his intuitive choice will get him more private time. Sorry for the kitten interruption, but let's continue. How much impact does Abraham, the man of honor's choice, make? Does it really make a big difference? Let's quantify Abraham's goal. Abraham basically wants to increase the capacity of the so-called saturated configuration. So what's a saturated configuration? It is a configuration of the urinals such that the next peer will have to or be forced to violate some existing peer's privacy. For example, if you take the last urinal of the three, it is not a saturated configuration. But if you take the middle one, it becomes a saturated configuration. Similarly, if you take the last one of this configuration, it's not saturated, but if you take the fifth one, it becomes saturated. To quantify Abraham's goal, let's define ANI as the number of peers in the saturated configuration if Abraham, the man of honor, picks the ith urinal at the beginning. Let's calculate a few simple ones. A11 is 1, A21 is 1, A22 by symmetry is also 1. The first time Abraham's choice will make a difference is when n equals 3. A31 is 2, but A32 is 1. We can still attempt larger n's like n equals to 5. For example, A51 is 3, A52 is 2. Well, things get complicated very quickly, so let's write some code for it. When was the last time you saw printed code? Sending human to the moon? Now we send Abraham to pee. First, we use a NumPy array to represent the starting configuration. Then, in a while loop, we keep searching for our candidate urinals for our next peer. When we find an unoccupied urinal, we find the left distance and the right distance to the neighboring occupied urinals. A trick here for the urinals on the boundary is to set its left distance or right distance to be infinity to indicate that they have no neighbors whatsoever on that side. Next, we look to the left of our potential candidate. We will stop searching when we find the first occupied urinal or we hit the wall. Otherwise, increase the left distance. Do the same for the right-hand distance as well. By picking the smaller of the left distance and the right distance, we get the shortest distance to the first occupied urinal of this candidate. Remember, The distance can be 0, so we need to filter out those unqualified positions. If the candidate's dictionary is empty, it means the configuration is saturated. It's time to break the while loop. Otherwise, we find the best candidates with the largest interpersonal distance. If there are multiple best candidates, we just pick a random one. I once again ask for your patience. Please allow me to prove this later that this doesn't affect the value of ANI. Notice that we can also return the configuration easily. Let's put the code into work. If there are 30 urinals, this is how Abraham's choice will impact the saturated configuration. So if Abraham is really a man of honor, he should choose the first one, the 14th, 15th, 16th, 17th, or the last one. In this case, our man of the end, Dave, is also a man of honor. Well, this pattern is not always true. When n is 100, the W shape changes to M shape. The man of the honor's choices are roughly around 1/3 or 2/3 of those 100 urinals. The technical requirement to be a man of honor is to know which urinal to use. Is there a consistent choice? The example we just saw suggests that there is no such a simple choice. Nowadays, it's hard to be a man of honor, even in the restroom. Abraham has to adjust his choice all the time. Guess what? Our man is determined. Abraham is just going to choose the I that maximizes ANI for any n. Abraham just wants to see how many additional peers he helps to pee with privacy. To evaluate the effects of Abraham's action, we need a benchmark. So let's use Dave's stay at the end strategy as a benchmark strategy. And based on that, we calculate the difference between Abraham's man of the honor strategy and Dave's benchmark strategy. The white trajectory represents the best Abraham can do. The yellow trajectory represents Dave's benchmark strategy. It seems that the two trajectories are bounded by two straight lines, one with slope of 1/2, another 1/3. The difference becomes more significant if we compare the efficiency. For example, Abraham single-handedly improved the worst performance from roughly 1/3 to around 45%. Before continuing our analysis, a round of applause for Abraham. It's time to fulfill my promise. Let's prove that the random choice in the algorithm doesn't affect the final value of ANI. You know what? Let's be more ambitious. Let's derive the closed form expression of ANI. We begin with a simple claim. At least one of the first two pairs will occupy an end urinal. There are three cases. In the first case, Abraham, but it feels more natural to say you pick one end urinal as the first pair. So of course, the second pair will pick another end. It is clear that our claim is true. The second case, you didn't pick an end urinal, but n is an even number. So you have to be on 1/2 of the urinals. Of course, the second pair will pick the end urinal on the other side. The third case, you didn't pick an end urinal and n is an odd number. The only difference between case 2 and case 3 is that you have the chance to pick the exact middle one. However, in that case, the second pair will just pick an end urinal on either side. By enumerating all possibilities, our claim is proved to be true. Let's take a closer look at our configuration with two occupied urinals. Without losing generality, let's assume n is 7 and the leftmost urinal is the one guaranteed to be occupied. In this discussion, we also have three cases. The first case is that both ends are occupied, which comes from calculating AN1. We now have 5 unoccupied urinals enclosed with 2 occupied urinals. We can define a new notation, Bn, as the number of possible middle pairs given both ends of n urinals are occupied. What do we have? ANI is Bn plus 2 when I is 1 or n. The benefits of introducing Bn will be reviewed very soon. The second case is just a variation of case 1. One of the 2 pairs picks the second or the second to last urinal. By doing so, the rightmost urinal is basically wasted. Therefore, Bn becomes Bn minus 1. So we have ANI is Bn minus 1 plus 2. It is time to address the general case. For example, this configuration will happen if the first pair picks not the last, not the second to last, but the third to last urinal. When the third pair walks into the restroom, he has 3 equally good choices, the third, the fourth, and the last one. By simply eyeballing this configuration, we can see that his choice actually doesn't matter. But let's prove this systematically. To do that, we need our second claim. Any pair will separate the configuration to 2 non-interacting configurations. For example, if someone occupies the rightmost urinal, it has no effect over the urinals to the left of the 6th urinal. The interaction distance between pairs is just 1. In physics, the famous Ising model describes exactly the same thing. A chain of up and down spins interact with each other, and the interaction distance is just 1. With claim 2 proved, we can focus on the configurations without occupied urinals in the middle. All the left is to prove our claim 3. If there are pairs on both ends, the randomness doesn't matter. There are 2 possible cases. The first case, n is an even number, let's say 2k plus 2. Then there will be 2k unoccupied urinals in the middle. By symmetry, the 2 central ones are equivalent. You can just redefine left as right, right as left. The new configurations are the same. If a subconfiguration after the splitting also contains even number of unoccupied urinals in the middle, this logic will continue. How about odd number of unoccupied urinals in the middle? Well, it's actually easier. We don't even need the argument of symmetry. The central one, or the middle one, will be definitely taken, because it has equal distance to both ends. We have 2 identical subconfigurations. The moral of the story is that you have a starting configuration, let's say it's even. You split it again. Every splitting means there is a new pair joining. But if it's even, we have the argument of symmetry. If it's odd, there is no randomness at all. We can now derive the general formulas. It is 3 plus bi plus bn minus I plus 1. With the most general case completed, our expression of ANI is now complete for all possible cases. You may wonder, why do we need to introduce a new notation Bn? Bn has a unique advantage. Because if you put a pair in the middle, you naturally have 2 Bn expressions of a smaller n. This power of recursion is not something that ANI is capable of. Let's derive the recursive relationship for Bn. If n is an odd number, then the third pair will occupy the exact middle one, which leads to 2 identical smaller configurations. We have Bn is equal to 1 plus bn plus 1 divided by 2 plus bn plus 1 divided by 2. If n is even, then we will have two different sized configurations. But because of symmetry again, we can just treat the first one as a smaller one, the second one as a slightly larger one. We have bn is equal to 1 plus bn divided by 2 plus bn divided by 2 plus 1. If you want, we can also unify these two expressions. We can introduce the cell and the floor operators. Cell basically means find the smallest integer that is greater than or equal to the operand, and the floor operator does the opposite. I feel really ashamed to admit that I don't find the following expression straightforward. The straightforward expression concludes our attempt of obtaining a closed-form solution of ANI. You can verify that it does agree with our naive ANI algorithm. Up to this moment, we have been working on figuring out the value of ANI, the capacity of saturated configuration. But that's not the end goal. Both Abraham and Dave would prefer to have a longer privacy for themselves. Take this saturated configuration as an example. It's saturated at its maximum possible capacity because Abraham has two neighbors while Dave only has one. If the following disappointed peers choose urinals randomly, I would anticipate that Dave has a better shot of maintaining his privacy longer. This suggests that maximizing ANI does not naturally lead to maximizing the time or the number of peers when your privacy is violated. Most of the time, Abraham has to choose one urinal that has two neighbors. In the post-saturation stage, this is a disadvantage. Let's define VNI as the number of peers when your privacy is violated if you choose ith urinal at the beginning. Then, it's natural to define the difference between VNI and ANI. Let's call it RNI. It is the number of peers that come to P after saturation until your privacy is violated. The notation R comes from the stage name random fading stage, which is just the post-saturation stage. In summary, we have ANI plus RNI equals VNI. The introduction of the name random fading is actually our third and last assumption. When a peer walks into a restroom knowing he will have to violate someone's privacy, we assume he will just pick an available one randomly. Take a look at this simple example that the same ANI value does not lead to the same VNI value. Let's say you pick the second urinal among the four, so A42 is 2. The third peer will have to violate your privacy, so R42 is 1. Therefore, V42 is 3. However, if you choose the first urinal, A41 is therefore 2, but the third peer has a 50% chance to choose the second one and 50% chance to choose the third one. What we have is a statistical expectation. It is 1/2 plus 1/2 times 2, which is 1.5. So V41 is 2 plus 1.5, 3.5. Indeed, there is an advantage by only having one neighbor. Wait, Dave is not the only person that has the advantage. Dave has the advantage of only having one neighbor in the post-saturation or random fill stage. But Abraham has the advantage of securing more happy peers to be in privacy in the pre-saturation stage. Why is maximizing ANI an advantage? Because you deterministically allow more peers to P. I will leave the detailed proof to you, the viewer, but now what we have is a clash of advantages. Who will win, Abraham or Dave? Although I admire Abraham's honorable action, my intuition tells me that Dave's advantage is just bigger. What I'm going to do is to pick an n such that Abraham has the biggest possible efficiency lead. One such example is when n is 97. So A 97 33, 33 is Abraham's choice, is 49. It's actually more than 50% efficiency. Well, Dave picks the first urinal. A97-1 is only 33, so Abraham has a lead of 16. Our next goal is to calculate R97-33 and R97-1. For Abraham's case, there are 97 minus 49, 48 unoccupied urinals, and among them, 2 of them are Abraham's neighbors. Therefore, the very next pair has a chance of 2 over 48 to be Abraham's neighbor. This is our first possibility. If this pair doesn't pick one of Abraham's neighbors, which has a probability 46 over 48, the next pair will have a chance of 2 over 47 to be Abraham's neighbor. We can continue the enumeration by multiplying the probabilities for this chain of events. The idea is actually very simple. Abraham dodged the first pair in the random fail stage, then the second pair, the third pair, etc., until someone takes the urinal next to him. At the end of the day, we have 47 possibilities. Notice that I already multiplied the corresponding outcome at the end of the expression. To get the final result, we need to sum those 47 terms together. Pay attention to the upper bound and the lower bound. We can write it down concisely. You can calculate this summation using Wolfram alpha, and the result is 49 over 3. Using the same trick, you can calculate R97-1 for Dave. I'll just be quiet here so you can take this as an exercise. We don't need Wolfram alpha this time. The result is 65 over 2. It is time to clear the mystery. So Abraham will have an expected number of pairs of 65 1/3 when his privacy is violated. On the other hand, the number for Dave is 65 1/2. Dave's privacy is longer by a margin that is so small, not 1/2, not 1/3, but 1/6. With a little bit examination, we can write down the exact formula for V and I. I understand why many people say mathematics is boring or useless, because this result is shockingly intuitive. You always go to the end if you want to enjoy more privacy. The smallest difference between these two curves happens when n is equal to those numbers, and 97 is one of them. Make no mistake, I'm not saying that Dave's choice is bad. I go to the end as well. But Abraham can single-handedly, significantly improve his fellow peers' experience. We need more Abrahams. My friend, that's something only mathematics can tell you. Thank you for watching. I will see you in the next one.